Hi, my name is Łukasz Langa.
Hi, my name is Pablo Galindo.
And this is the Core.py podcast, a new podcast where we discuss internals of CPython and our adventures in making a new version of your favorite programming language. This time we focus on the part of Python that reads your source code text and converts it to an unambiguous representation that can be compiled into executable form. We will be talking about parsers.
Oh, I thought we were going to be talking about the magical gnomes that we have in CPython that transform the text into programs.
Yeah, well, this technology we're changing over the years. Obviously, the sensibility towards gnomes changed over the years, and now we cannot afford having them anymore because, fair wages for all those gnomes, for all those instances of Python running all over the world. Like, that would ruin us.
We employ goblins now. They're much cheaper.
Joking aside, from the very first version of Python 1.0, which now turned 30 years old, you had technology that was basis of how Python is parsing source code text until super recently when you came along, Pablo.
Yeah, the destroyer of parsers.
Well, destroyer and rebuilder, like Phoenix from the ashes.
I will put that in my curriculum. Nice.
In any case, if you are wondering how did Python 1.0 look like, you can still download the sources for it and even binaries for some operating systems that you might have luck actually executing. I didn't, but you can try. So if you go to python.org to downloads, then to all releases and click on view older releases, you're going to find all those binaries, but also a link to older source releases, and that includes Python 101. This is mostly an exercise for you to just look inside and see a much simpler version of the programming language, but surprisingly, a lot of the things that we now take for granted in Python were already there from day one, essentially.
Right.
Yeah, so the original 1.0 parser and grammar was using a handwritten tokenizer. So this is where we actually start getting input from the user. It can be either from a file or it can be from standard input. And in fact, we even had a hacked prompt mode for the interactive REPL that survived until 3.12.
That was what I was going to say. What do you mean had? Like this make it sound like in Python, 2.0 was gone. No, man, this is like still for today. If someone is using 3.12 these days, they still have the hack.
Yeah, there's an open PR to actually get rid of that.
Yeah.
So it's going away for 3.13, but yes, it survived. So the thing that implemented the interactive REPL lives to this day in 3.12 in the tokenizer.
Right.
But before we get too deep into weeds, let's stop for a second and just ask the fundamental question, which is, what even is a tokenizer? What is a token? So when the interpreter is receiving input, what it receives are bytes, right? And it doesn't really know what those bytes represent. So first, it needs to establish some encoding that will allow it to understand whether a single letter takes up a single byte or two, and which one is which. After that, it can actually now understand that you are providing Python with a keyword like import or return, or maybe a number like 45, or a variable name like Pablo. No. And then it categorizes those things as tokens. So if we got a plus, it will tell us, oh yeah, you got this plus sign. So obviously the tokens that are recognized by Python changed over the years. We didn't have async and await in the early days, but we did, for example, have print as a keyword because it was a special statement. But what I want to talk about right now is some peculiarities in what the tokenizer includes. And there are some surprises there. The most trivial surprise that I don't know, it's probably because I'm Polish, but every time I saw the caret sign, so the inverted V character, I was confused about how it was named, which is Circumflex. I was always like kind of flabbergasted, like, which one is that? Circumflex? What is this? But apparently that's the official name for this character in the ASCII standard. So it's still called that today. But every time I look at the tokens and I see circumflex, I need to spend 2 seconds thinking like, which one? Wait, what? Like, which one is that?
It's a circular flex.
Yeah, like it's I'm not sure, like, is it a body part or is it like a condition? Like I don't know.
Cuneiform character.
Yeah, for me it's weird. There are tokens in the tokenizer that are invisible, and 2 invisible ones that, Guido would tell you Python will never have those are braces.
What do you mean? What do you mean braces? Do we have braces, Łukasz? What is this?
We had them all along.
No.
There are tokens called indent and dedent that allow us to actually organize code in blocks, right? We need to understand that there was some semantic indentation for a block and that this indentation ended, right? So we dedented back to the previous level. So those are implemented in the tokenizer as specific tokens. So the tokenizer understands that you are indenting by some amount, like 4 spaces and whatnot, and it will now emit a single indent token for that. And if you dedent back by those 4 spaces, it'll emit a dedent token with that.
But wait a second. It's time for Pedantic Pablo.
Let's go.
Okay, so I have here this argument a bunch of times, and it's true, but it has gone too far. And I know you popularize it, this idea of like, oh, Python has braces, haha. Is here. You can see them run Python -m tokenize, and then you will see indent and dedent. And it's true. What you say is true. But technically, the key here is that those are dynamic tokens. So there is a lot of like interesting things that we are not going to discuss here about like if Python is context free or not and all that stuff. But like one of the key things here is that the tokenizer will emit indent and dedent based on context. So like braces, normally when you program in C++, if you see the character, that is brace, like open brace or close brace. And you can put them more or less whatever, right?
Right.
But Python will emit those dynamically. And those, like the decision, if you indent one or the other, depends on the context. And actually, you cannot just start technically the tokenizer in a particular point and then keep going and emit the correct tokens there. So that makes them, it's a category called non-context-free tokens that we do. Traditionally, we have put all of this crap in the tokenizer. So yes, we do have indent and dedent, and we can call them braces, but there is like some pedantic information behind that. It's kind of like not really normal braces, but
sure. But this is sort of hair splitting because it only becomes important if you are implementing some text editor that handles text selections, and you have to figure out whether you can clearly dedent or indent what the user selected, or if you're implementing black and you have format on and format off block comments that do something specific, and there's weird behavior if those comments are not at the same level of indentation. And we're going to talk about black later. But now I still have a bunch of fun facts about the tokenizer, because it's like...
Are you implying that black is not fun?
Well,
sorry, I will shut up.
If you want fun, you need to find something that was named after a comedy group. So let's focus on the tokenizer. Let's go.
Right.
There used to be backquotes, so-called backticks in Python.
All right.
Did you know about this? So the key that has the tilde on it as well, like that was used by Python.
No.
Yeah.
I have only seen, because Anthony Shaw had this crazy idea of having like test names that contain spaces, and he kind of hacked the tokenizer into other the backticks to allow that. So you can make a test function in Python that has spaces. So instead of saying Łukasz _cool _test, you could say Łukasz cool test, and then you put backticks, and it's kind of like a function that has spaces. But that is the only time I have seen those, which is obviously non-official.
Right. So there are many ideas how you could use the backticks, because they are no longer used by the tokenizer. That was removed in Python 3.0. So since this is a free character now, there are many ideas what we could use it for. Obviously, most of those are terrible ideas, but people still actually share them.
Like the $, man, everybody is after that one. It's like,
yes,
we can use it for so many things.
Right. So the question is, what was the backtick used for when it was part of Python?
I don't know. I don't know the answer to this, which is surprising.
Yeah, so
Strings? No.
it's just a shorthand for getting the wrapper.
Okay.
Yeah, not extremely useful in my mind. What I thought this was doing was to allow you to shell out, right? So just to call some sub-process and get its output. I think Perl is doing this, which is why I thought
Well,
that.
like IPython does sometimes, like when you do like exclamation mark pip install something. Like,
Right, but that would be in the form of a string that starts and ends. So
Right.
we know that if passed as an argument to a function call, like this is the command that we're shelling to. It's still not perfect because there's no way to communicate what to do with error handling and how to pipe output and input. So obviously this is not actually what Python did.
right.
It was just a wrapper, and it was kind of argued at the time that it was useful to have this because it was faster than calling wrapper. Since wrapper is a function call, it's slower. Yeah, of
The
course.
all excuse.
But Łukasz, those 2 nanoseconds are very important.
Yes. If you wrapper in a loop, like that would be a big performance gain. And we're all about performance, so maybe Backticks should come back.
We should JIT the report.
Yeah. So question. In the tokenizer, where are the tokens that represent the white space and comments?
Very good questions. Which tokenizer, Łukasz?
Well, the main Python tokenizer that Python is using to actually compile your code later on, like the thing that gets passed to the parser that later gets passed to the compiler.
Right.
So on that pipeline. So what happens to comments then?
Then which version, Łukasz? Sorry, you are dealing with Pedantic Pablo. You cannot escape. Which version? Because this has changed.
Yeah, I know. Like we cannot go back all the way to Python 1.0 since we cannot run it and you know a little about it. So let's just say Python 3.8. Specifically, I know this is the version that is still like untouched by Pablo's parser
I was going to say
touch.
to our listeners that they cannot see this because this is the magic of the podcast. But Łukasz is looking at me like, can you stop doing that? I'm very sorry. Okay, the old one. Yes, sorry. Yes, they are gone. I know that answer because I also destroyed that. They are gone. Yeah, the tokenizer says, voila, what comment are you talking about? It literally skips over them. For comments and for white spaces, it means nothing.
Yeah.
Actually, for comments, it's even funny because like it skips over them in ways that are non-recoverable, which was very painful to fix.
Yeah, I can imagine. So on that pipeline that starts with some bytes on the input that then are tokenized, we get to a parser. So something that organizes those tokens in some data structure. So let's talk about the parser right now. And big boys of programming generate parsers by hand, just writing them manually.
Right.
In Python, we don't do that. And we didn't do that even in Python 1.0. There was already a generated parser, which around that time had just 700 lines of code. And these days, we have more of that. And we generated it already from a grammar file. And that one was so cute. In Python 1.0, it was barely 50 lines of code of actual grammar. Like there was like almost twice as much just comments, but the actual grammar was very short.
Amateurs, like even this file on Python 3.5 was just enormous, man. Like it's just enormous in gigantic file.
Yes. But again, we need to step back and explain what a grammar even is, right? So
Right.
essentially, this is a list of specialized regular expressions that each describe a so-called production, right? So all of those productions are subsets of what you can express in the language. So the format that Guido chose for the Python 1.0 grammar, and that was something that survived until Python 3.8, was a customized Backus-Nauer form. So that's kind of hard to show in the podcast form, but in essence, the file is a list of productions that, for example, say that file input consists of many new lines and statements finished by an end marker.
Right.
So each statement in turn is either a simple statement, so it's the name of a different production, simple statement, or a compound statement. So the grammar then specifies exactly what this compound statement is and what a simple statement can be, and so on and so on. So for example, a simple statement would be either an expression, a pass, a del, an import, a global, a print statement, because this is still Python 1.0, or a flow control statement like break, continue, return, or erase, and so on and so on. And now the key here is that you can compose those productions using references between them. So as I said, file input consists of many statements, and each statement is either simple or compound, and so on and so on. So it is a form of, well, let's call them Russian dolls. So like they are nesting.
Wait a second. Pedantic Pablo has something to say.
Welcome back, Pedantic Pablo. We missed you.
Okay, yes. Always happy to be here. Russian dolls is a bad mental image because the rules can loop back. Like so Russian dolls gives you the idea that, you know, one nest inside the other and then there is the smaller one. But what can happen here is that the smaller one calls the big one again. So it's like a 4-dimensional Russian doll, I suppose. So when you go to the smaller Russian doll, you can go back to the bigger one and loop forever.
Yeah, for example, you can have an if statement that has this so-called trailer block, so like this entire inner block, and that inner block contains another if statement, right? So
or like the classic one in Python that is the most dangerous one is that the one that we call atom, which is technically the smaller piece that can be a number or a variable, but they can also be a parenthesized expression, and that can go all the way again to be anything, in particular another atom.
Right, sure.
And then there are more ways to loop back, but yes, it's not like technically a tree.
Yeah, okay. So thank you for your service, Pedantic Pablo. But now let's talk to Fun Fact Pablo.
Oh.
So did you know that in Python 1.0, we had a reserved but not implemented keyword called access?
What? What do you mean?
There was a statement that used the keyword access.
No. I have read that file for years and I have never seen that. Oh, this is in 1.0.
Yeah.
Oh man, what is this doing?
Yeah, so the docs say this statement will be used in the future to control access to instance and class variables. Currently, its syntax and effects are undefined. However, the keyword access is a reserved word for the parser. So that was Python 1.0.
But this is the feature and it's not here. They lied to us.
Well, only to an extent, because there was a future from the perspective of Python 1.0 that comes before where we are today, where this statement was actually implemented.
Like a fully featured access or just the parser says that is here.
So yeah.
Like in the sense that it's doing something or it's just being accepted by the parser.
Oh, so I didn't go that deep. I know it was accepted, and I know usage of this was in the standard library, because this is how I found out about this.
What is so important to require the keyword access, Łukasz?
Well, you can find out by yourself by downloading Python 1.3 sources and opening the standard library called wave.py.
What is that?
Well, that is called
Wave.
literally stuff to parse WAV files. So in there, you're going to find a line that literally says access asterisk colon private.
No!
So you could say that everything in that block later on are just private members. So for a while, Python planned to have access levels like Java.
People were not adults at the time.
So we would have private and protected and public and this sort of thing. So that was accepted by the parser that was there.
They start with underscore even.
No, you know what was even more disgusting?
This is quite disgusting. I mean, sorry for everyone that participated in this.
The disgusting thing is that obviously this is super not Pythonic. So it was something that was removed after some point because it lost to this consenting adults principle, where like we just mark things that are private with leading underscores, but if you really need to use them for whatever reason, like debugging, you can access those. But you know, in those times, you could actually mark this. I don't know if that would actually reject those accesses at runtime. I doubt that was implemented, but maybe. Like, we can ask Guido later.
No. Sorry, wait a second, dear listeners and Łukasz here. I'm doing this live, so this is true, like detective work right now. So I'm looking at this rule, and I'm extremely impressed by the following fact. So technically, you mentioned that you can do access star, but apparently you can put whatever.
Yes.
Like you can say
Any
access as, and that works. Like so you can put whatever there. You can put access Łukasz. The parser will eat that.
Yeah.
And not only that, I'm checking the compiler, and actually it's compiled. This was fully featured, and it only accepted public, protected, and private.
Right, but note that those are not keywords. So this was the compiler that limited what was accepted there. The parser accepted whatever.
No. It accepts also read and write.
Yeah?
Man, this is fantastic spelunking. It accepts 1, 2, 3, 4, 5 things. It accepts public, protected, private, read and write. But read and write were like weirdly implemented. Like I don't think they were fully there. And this is
Yeah, I don't know, man.
wow.
The only thing I know about this is that this was an early example of us contorting the parser because obviously we couldn't just now have keywords that are private, public, read, write. That would be super annoying for all the APIs that you would be writing. Like you couldn't have a method called read. That would suck. So the parser would accept anything that was after the colon. So if you had access star colon private, what it would actually say is like, oh, hey, for the parser, anything can go after the colon. Only the compiler had a white list, or how would you call it, like the accept list of those 5 words. And if you actually said Łukasz like on the right side, you would get a syntax error there, but it would not come from the parser, but from the compiler.
Right.
And this is a trick we did many times in Python. So over the years until Python 3.8, when we were growing the grammar with the old parser, those sorts of workarounds for the limitations of the old parser that we had were only growing. Like, you remember any examples?
Yeah, I do. Like there are there's so many that are super annoying. We actually there's going to be a question, Łukasz, in a second. So be prepared for your question of the episode. But let me think one of the examples. Well, I think async.io was half implemented also on the compiler, right? There was some checks.
Yeah, like for a while we had soft keywords for async and await, and I actually liked them a lot. Like Python 3.7 that removed this was a major pain for migration because a lot of legacy code in companies that included Instagram and Facebook like had just files called async.py, and you know, obviously there were like many keyword arguments called async, like there were booleans like equals true, right, or whatever, and now we had to rename all of this but maintain some cohesion. And obviously you couldn't automatically find everything. You could find most things, but some things would just come from JSON files or strings or other dynamic forms, and you know, you would only find this after you ran it in production, and it would crash in an ugly way. So yeah, like I didn't quite enjoy removing the soft keywords there, but at the time, we felt like soft keywords are a hack, that we will never have soft keywords because they're like, no, they're not true keywords. Like, who would do this?
Exactly.
And then with the new parser,
What a Spaniard.
we will only have new keywords that are soft keywords now.
We elevated the hack to a feature. We said like,
Yes, to an art form.
it's true. There is even the keyword module. Surprise, that thing exists.
Yeah.
And now it has this soft keywords attribute that will tell you that which ones are soft keywords. Łukasz. Surprise question.
Match.
Match.
In case.
That is incorrect. Actually, match and case are correct, but you are missing one.
Oh, so there is yet another one.
There's a third one.
Oh, so now there's type.
That's new. Okay, there is another one that you're missing related to match. It's related.
What?
Yes, match, case, and it's a single character.
What? No.
It's the underscore. It's the underscore.
Oh, the underscore is a keyword in the context of the pattern.
Yes, I'm not lying. In 3.11, if you import keyword and then you write keyword.soft KW list, because apparently writing keyword is very expensive, is underscore case unmatch.
Right, okay.
And in 312 is probably type as well.
I forgot the underscore. My career is over. Oh my God.
Your career is in danger. Let's say in danger. You can gain your career back later.
Good. So there's going to be some redemption arc later. So stay tuned for that. But for now, let's get back to parsers. So we already mentioned that the grammar is supposed to be context-free. So what does that mean? Well, there is a formal definition and full of math symbols and fancy language. If you are looking for that, look for Wikipedia or some literature, and then you can...
They want to impress their friends.
Right. For us, let's just say that a context-free grammar is a fancy term that essentially means that every construct in the grammar is built from smaller blocks from the same grammar. And those block structures are unambiguous regardless of how they are combined. It's only important for us to realize that context-free grammars have limitations over natural language. Like the necessity to use brackets in neat pairs. So you kind of have kind of the open parentheses never end or end, after something that you now introduced like another bracket pair and so on and so on. Like you need to actually have neatly nested bracket pairs. So for example, like my personal pet peeve about the English language is that the punctuation rules say that you should put outer sentence punctuation inside quotation marks, which I find just ugly and also just inconsistent. I just don't like this. It just, I just deliberately just write it in the other way since it makes more sense to me.
Yeah, that sucks. I'm not a fan as well.
Yeah, but that would not fly in a context-free grammar because that grammar would be like, no, you're inside the string. Like we're still ignoring what is there since it's not outer punctuation, it's inner punctuation. So imagine all those edge cases that we would need to introduce to support this.
I will hate it. No.
Yeah, right. That would be a stuff of nightmares. Like we already have one ugly thing that we need to support for strings, which is backslashes. So, for example, a \n is an escaped value that just means an actual new line, right? And there is a bunch of them that are defined. And even if you write a backslash followed by something that Python does not recognize, the worst that's going to happen is the tokenizer will emit a warning saying there is an invalid escape that you used, but the string is going to still be intact. It's fine. Like you made a mistake, you didn't know, but it works fine.
Right.
But if you put a backslash as the last character of the string, well, now you didn't close the string because backslash at the end just means we are in fact escaping the closing bracket. We are escaping the closing quotation mark,
right,
so that we can continue the string. So that breaks everything if you don't know about this. And this special value is even considered when we have raw strings.
Now there are more actually, because in 312 you can have an F string, which now it can open a bracket and contain arbitrary expressions, as you know, the changes I did, and that can continue in the next line. So now that edge case is 3 edge cases.
Oh yeah, because new lines now joined the edge cases. Yes. So
yeah, you can have technically this is very funny to say out loud. You can have a single quoted F string that contains a multi-line expression. So the string itself can spawn multiple lines even if it's single quoted.
Thanks. We hate it.
Yeah, language implementers hate him. Yes, that was implemented because that is the correct way. Anyone that says that is incorrect, I will show him 3 different compiler textbooks that give me the
Makes
version.
sense for the implementation. What it doesn't make sense for is when you are writing a code formatter and now you are faced with this question, should you then use the fact that this is possible and now explode the...
You are talking because someone did that. You know it, right? Like someone asked us like if they should do that.
So my personal opinion is that no. Just leave the inner expressions alone. But this is not something that is objectively decided. It's a subjective opinion. So obviously there's gonna have to be somebody who has a different opinion.
You can kind of do it.
Or says like, no, don't format it entirely. Just format it a little. And everybody has a different opinion of what a little means.
Oh, but then there's another edge case, right? Because if you add an equal at the end of the expression, then the debug expression
Yes.
changes because it's new line and blah 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 blah. You see,
Right.
the fucking computer science world is full of this. Like, it's just a void.
Right. But fortunately, we can draw from experience of previous specialists in the field and, stand on their shoulders through their literature. Like, for example, I first learned of compilers reading the famous Red Dragon book that is Compilers, Principles, Techniques, and Tools by Aho, Sethi, and Ullman. It's a very famous book, and I was pleasantly surprised that Guido used algorithms from the predecessor of this book. The predecessor was called Principles of Compiler Design by only Aho and Ullman. Ravi Sethi didn't join the team back then yet, in the first edition, I guess. And that book had a dragon too, but it was a green one this time. And Guido used those algorithms in the parser generator. So the program that is used to create the parser automatically from the grammar file.
The first one is green, and then the
Green dragon book.
Spanish dragon, actually.
So how is it Spanish if it's green? That makes no sense.
No, it's not about the color.
Should be red.
I'm colorblind, for instance, and I'm Spanish. That didn't explode the universe. Right? So no, it's not about the color. It's Spanish because the cover it depicts Don Quixote fighting with windmills, except that the windmills are a dragon. So, but the knight killing the dragon is supposed to be Don Quixote, which is, as you know,
that makes sense. Because the one I know was a red dragon that looks into the programmer, who is a knight, like through the computer screen. So it was like this. Also, this comic book kind of cover. It was very nice. Like I liked it a lot.
Right, and then the third one,
this other newer edition,
it's an aberration. It's horrendous.
Yeah, and that one is just this 3D generated like purple dragon.
It's AI shit before AI. Yeah. I'm very sorry for the designer, but
yeah, I agree. But let's get back to parsers. So we are saying this word all the time in this episode, but what does it actually mean to parse? Like, what is the functionality of the parser? What does it take and what does it produce? What does it do, Pablo?
Pedantic Pablo is in the door, so I'm going to not be Pedantic Pablo for this answer. But technically, what the CPython at least parser does is that the input is the tokens from the tokenizer, so it receives this plus, name, sum, keyword, and it transforms this into. It depends. It depends on the version. So technically, it transforms this into the most versions use. It transforms this into AST nodes, which is like an abstract representation of your program. It's kind of like a tree. Well, it's a tree. And it basically says like how your code is structured. So for instance, it says if statement. And inside the if statement, there is like body. And inside the body, there is like something like, well, condition, right? And then things like that. So the grammar itself it used to produce an intermediate representation called a CST that stands for concrete syntax tree, and that is something a bit more raw, but it has like information about, like, for instance, characters that are not really useful for like the information that the compiler needs, like commas, white space, etc.
Yeah, so white space, no, right? Because we were throwing it away.
But it could have white space or commas or things like that.
Commas that are sometimes just optional,
Right.
Or whether you used parentheses or not, like that would actually be in the concrete syntax tree.
It depends quite a lot. That is what is called concrete. Like you can have all of this or nothing. The CPython one drop a lot of stuff, obviously. But the idea is that, for instance, one of the big changes that we used to have is that the subgrammar for expressions, like especially the calculator grammar that we normally call, so plus, minus, times, and divided by, right? So that used to be flattened. The reason is because the way is parsed is basically like expecting like a continuation of a bunch of them. So in regular expressions, it will use like so one number and obviously 0 or more plus and another number, and that gives you like a list of things. So like number plus number plus number, like flatten.
Yeah.
But the AST need to be nested because you need to basically encode the order of operations. The AST doesn't know the order of operations. It doesn't know that times binds more higher level than plus, for instance, right? So if you have 1 plus 2 times 3, you need to multiply first and then add the 1, right? So that is represented in the AST by the level of nesting. So you will have plus, and then the left operand will be a 1, and then the right operand will be a times, and times will have 2 and 3, right? So that means that first you do 2 times 3, and then you add to the plus. But the order of operation in the ST is indicated by the structure of the tree. But the CST that the parser produces is flattened. It will be 1 plus 2 times 3. It doesn't know. So there is this transformation that needs to happen. So the parser, in summary, basically eats tokens and outputs an AST, which is the abstract syntax tree, which is this tree that represents your program that then the compiler will receive and it will transform into bytecode. We didn't used to have an AST actually. The compiler used to eat directly the CST, which was suboptimal, as you can imagine.
Right.
Because it changes quite a lot, and then you need to change the compiler a lot.
But if you looked at the parser until Python 3.8 inclusive, and also in 3.9 if you knew where you were looking, because it shipped with 2 parsers, right? So like, it was
minus X Old Parser is the
sneaky shit. Yes,
sneaky shit.
It had 2 parsers. Like, why have?
Well,
one?
it had more than 2 parsers, but yeah, you had 3 parsers.
Right. Yes, we're gonna actually talk about this third one later on. But for now, let's talk about the contents of the parser generator. If you open it up, you see finite automatons, non-deterministic ones, deterministic ones. Like, how are they all composing? What does that mean?
But what you're talking about is the parser generator, not the parser,
right. Yes. So this code which ends up generating what the parser is from the grammar file. So when you look inside, you're going to see there's NFAs, DFAs. I would like to understand what this is all about.
Well, so this is the process to generate the actual parser. So the first thing you do is generate these state machines, which are quite popular in computer science, right? It's like almost like a graph, and then you start in a particular node, and then you can end in another node, and then there is paths depending on the input. So you can have like a start, and then there is 2 paths, plus and minus, and then depending of the token that you receive, you will traverse the path through one or the other. And then there is 2 of them, the DFA and the NDFA, so the deterministic and non-deterministic. The first being produced is the non-deterministic. And the reason is non-deterministic is because you can have 2 different paths for the same token, for instance. So you can have, you are in a particular state, let's say state 1, and then there is 2 paths for the plus symbol. So if you have a plus, you can go first one, but you can have a plus, you can also go to the second one, and that goes to a different place.
Yeah.
And that is what is called non-deterministic, because you don't know which one you need to choose. And then technically there is another source of non-determinism, which Python didn't have, because Guido was a bit clever over the design, which is called epsilon productions, because we like to say shit, but that basically is called an empty path. There is a path that you can follow by free, like even if you don't have any input, you can choose all that path always. So it's ambiguous because you can choose anything or the epsilon production
or this
path.
empty one.
And then there is an algorithm that a lot of people need to learn to pass the compiler's course in their university, which is called PowerSet simplification, which doesn't simplify anything. It creates a bigger shit. Because it's the number of nodes in the NFA, the non-deterministic one, is n. This algorithm creates 2 to the power of n nodes. So it's not good. So it makes it deterministic by basically grouping them together. So let's say you have a plus, and then you go to the node 1, and then you have another plus that goes to node 2. So what this will do is that it will group node 1 and node 2, and it will call the cool node, and then it will only be 1 plus, right? So plus will give you to the cool node, and it will apply this the algorithm is a bit complicated to explain in a podcast, but it will basically group these different universes that you can traverse to, right? So you can traverse to the first one and the second one, and it will group them, and it will create like superset of nodes, right? So
right.
One node in the new world will be multiple nodes in the old one.
So that's what Python 1.0 was actually doing. And then we had to use some heuristic to prune this
monster. Yes. 2 to the power of n.
Yeah.
Shit.
And
by the way, funny enough, that algorithm had an error condition I fixed. It never triggered, obviously, because this only ran on the Python grammar, and the Python grammar was quite simple. But it had an error condition that it could never finish.
Yeah.
Like the trimming could go into a loop forever.
Oh, that's interesting.
And so it was an academic bug fix, because it's a bug that it was never happening unless you change the grammar to make it happen.
Uh-huh.
Yeah, but the algorithm was incomplete. Yeah.
Interesting. Okay, so the NFAs and the DFAs, those are when you are taking the grammar file and generating the parser.
Yes.
So this is what happens. And then what you are arriving at is a parser. And that can be, say, LL1 parser. So that means it's reading left to right, and it performs leftmost derivation, and it uses one token from the future, air quotes, that could be used to disambiguate what production the parser is now looking at.
That's key. So that's the part that makes that I wanted to correct you from 15 minutes ago, which is that LL1 grammars are ambiguous. So you say that they are not ambiguous, but in truth they are. And this is it has to be with this one. This token for the future, as you mentioned, what it means is that when the grammar needs to choose, so that when this automata needs to follow the path, and need to know which of the rules, imagine that you have 3 possible rules to follow. It needs to know which one it is. It's only allowed to check the next token, right? So it needs to know which rule is going to be if only by looking at the next token. But the problem is that there are grammars that you can give where the next token is not enough to know which one of the alternatives will be. You will need more tokens, and that will make the grammar ambiguous. So obviously, if you don't do it, it's not ambiguous. but technically, you can do it.
I see what you mean.
Yes.
Right. So LL1 grammars are meant to be relatively simple, and yet Python's one grew to be relatively complicated. So there were some hacks in the compiler to catch syntax errors that were impossible to catch inside the parser itself, like what is allowed on the left side of an assignment. But let's get back to LL1. Like there's 2 L's there. So what does the second one, leftmost derivation, mean?
That means that you start expanding the rules from the left part of the expression. So when you have your production and then you say what your production is, I don't know, expression plus another expression. So it will mean that it will start expanding the left expression first, and then it will parse the plus and then the right expression.
Right, but some of the programming languages out there actually use rightmost derivation parsers, so LR parsers. That sounds kind of weird to me. How do you derivate the rightmost rule?
There is we will need another podcast for this. There is a lot of consequence of the L and the R. One of them is that one is normally is top down, the other is down to top. So one of them requires to like the leftmost derivation requires you to expand until you end in a non-terminal. So 3 is a terminal because it terminates there, like 3 is 3.
Yeah.
But like if condition is a non-terminal because like you need to expand if condition to know what it contains, right?
Yes.
So that a leftmost derivation will require you to expand the left constantly. So if you have a rule that is recursive on the left, so for instance, you say expression is an expression plus, I don't know, an item.
Yeah.
So it will start expanding expression. But what is expression? An expression plus an item. But what is in an expression? An expression plus an item. So it will start expanding expression. So technically, you cannot have what is called left recursive rules. Which are very handy because literally the calculator grammar, which is embedded into Python and many other things, is really, really well written when you do it left recursive. But you need to hack around to not make it. But an LR parser will start parsing the right part of that expression first. So you can disambiguate a bit easier. It's just that you will kind of invert the 3 depending on the parser. But
yeah,
it's easier to write left expanding parsers. So the L is easier than the R normally. A lot of parsing implementers probably will jump at me for this statement, but normally it's easier. Actually, the LL1, funny enough, the LL1 parsers normally they are called close, because you can implement them with a lookup table that normally you learn how to do the lookup table. And it's very funny because the way it was written in Python, the way we wrote it is a non-standard way to write LL1 parsers. But interestingly, he chose a bunch of like conditions. In particular, the most important one is that he didn't allow epsilon productions. So you cannot say that the empty string is something. Like you cannot have a rule that produces the empty string. A rule must parse something. So you have like atom, it has to be a number, a name, but it cannot say, oh, the empty string is valid. So with that restriction, the LL1 parser becomes not only much easier to write, but also much faster, and you can do this automata business instead of the table, which is much better for producing them. So it was quite impressive to have that. There is another restriction that is a bit difficult to explain, but this is the important one.
Nice. Right. So Python likes things that are good, and despite what the Zen of Python says, we duplicate them. So very early on in the standard library of Python, you already had a list of tokens, right? So what are the possible tokens that are recognized by the Python tokenizer? So there was a library just called token.py, and it just listed those. And soon after, we grew to have another tokenizer, actually, like implemented in pure Python, that would emit those tokens if you needed to write some Python library that needed a tokenizer. I don't know the history behind that. It does seem a little strange to me, like to maintain both. I guess it was for performance, sure, but
for performance?
Yeah, because we wanted the main tokenizer on the hot path of reading your source code to be as fast as possible, so it wouldn't deal with comments and whitespace. But the pure Python one could, right?
Right. The tokenizing in the standard library, it was and is still used by many tools like Flake8.
Yeah.
So there is a bunch of things there. Like one of the reasons that the implementation, I think the reason is because they didn't want to expose the C1 just in case there is some brutal changes to not have backwards incompatibility or something like that. But also because exposing the C1 is a bit complicated. We did that in Python 3.12, so now there is only the C1 that is exposed. But the Python one had a bunch of weird stuff. Like particularly one of them is that it emits whitespace tokens.
Right.
So the Python one will not only emit whitespace token, it will also emit comment tokens. So it will tell you like there is a comment here, right? And so you can reason about that. But also the whitespace tokens can be two kinds of whitespace tokens.
Right.
If I recall correctly, one of them is semantic whitespace and the other is non-semantic whitespace. So there is the new line token and then there is the NL token. And one of them means that it's a semantic new line, which is a new line that it will make a change in the parser. Like if you don't have that, it will be a syntax
that's
error.
a long one, a new line.
Right.
Yeah,
And then NL is a non-semantic new line, which is like you just added a new line because you like it. Like so you say if something, then something in the body, and then you do new line. That is an important one because that is the dent one, right? That is important. But then you can do new line because you are stupid and you are like to add many new lines. Those last ones are non-semantic ones because you can drop them.
Have you met me? I'm Pedantic Łukasz. So
Pedantic Łukasz.
Right. So the blank line use case is true, but the thing that I think this NL thing was actually added for was all those new lines that are inside expressions that can be multi-line. Like if you have a parenthesized pair, some brackets, and you have new lines there, like those are the NL tokens, because you need to tell the tooling that wants to do something with your source code that there are in fact new lines put there, but that is not the new line token, as you said, because this one is not about splitting things semantically. It's about code organization by the programmer, right? So it's within bracket pairs.
Right.
But yes, you also have those NLs after the first new line token was sent when you use multiple blank lines.
Right.
Yeah, and as you said, some tools were using this tokenizer. However, that was just part of the solution, since if you wanted to have any tree later on, you had to build it yourself. But not only that, this tokenizer implemented how the programming language works for the version of Python that you were running the tool with. So Flake8 running on, say, Python 3.4 could only parse Python 3 for source code, which was not perfect. It would be better if we had a tool that could parse multiple Python versions, right?
Right.
And Guido found himself needing a tool like this himself when we had this big debacle of how do you move from Python 2 to Python 3. The initial idea was to use an automated tool called 223. And that tool was supposed to just translate your Python 2 program into a Python 3 program. This obviously now hindsight is 2020. 223 didn't end up being super successful since people weren't ready to abandon Python 2 in just one fell swoop. Plus the tool was somewhat limited, but the way it was implemented was actually having a long-lasting impact on the Python ecosystem. Namely, it took the Python-based tokenizer we already had in the standard library and modified it. So now we had 3 tokenizers. But the third one was magical because it ran on Python 2. It could parse Python 3 grammar, and ran on Python 3. It could parse the Python 2 grammar, so that the magical 2-to-3 tool could actually work from both ends of the bargain. So from both ends of the transition. We needed to have a tree, but not the abstract kind that eschews all details about how the code looks like, because the entire transformation that 2-to-3 is doing is supposed to be invisible to the user in terms of leaving alone all the blank lines, all the formatting, and obviously the comments, some of which were really important, like the ones that actually specified which encoding was used for a particular source code file.
Right.
So to support this, Kaping and Guido wrote a library called lib2to3 that supported pluggable refactorings like changing imports or the famous print statement into a print function, or modifying methods on dictionaries from their old counterparts to new ones, and so on, so that you could transform Python 2 code to Python 3 code. This library included a concrete syntax tree, so this variant that actually has all the tokens spelled out, including whitespace and comments. But it also included this library of over 50 fixes for the renames in the standard library, and how filter was moved, and how imports are now different, and the except statement doesn't allow you the comma anymore, and the exec and exec file are different, and so on and so on.
Right.
So even though the tool itself wasn't successful, lib2to3 was. So most migrations to Python 3 used a tool by Armin Ronecker called Modernize, which was like 2-to-3, but instead of writing a Python 3 only variant of your code, it replaced the Python 2 constructs with imports from 6 and other things that would work on both Python 2 and Python 3. So ideally, then you could still run Python 2 in production for a while, but unit test on both Python 2 and Python 3, and at some point actually make that switch over. So that was the first very successful use for lib2to3. But then also Google's auto formatter for your source code called YAP started using lib2to3.
But why we will need that, Łukasz? Why is that
So
needed?
that was needed because a tool like YAP needed to be able to format code that is of a different version of Python than the Python used to run the tool, to execute the tool.
Right.
And, obviously 2-to-3 wanted to be able to do this in a way where you could run the tool from Python 3, but you were literally translating Python 2 source code into Python 3. So that had to be like explicitly a feature when they were designing 2-to-3, because otherwise the tool would not be able to work at all.
Right.
So funnily enough, because of future imports, there were a bunch of variants of Python 2 grammar. Like you could use the from future import print function, and you could use a new exec form, and so on and so on. So lib2to3 had to ship with multiple variants of how to parse Python 2. And then comes along a guy who contributed to YAP, who tried to adopt YAP at his own organization, which didn't quite work out. That's a different story for a different time, I guess. And decides to write his own formatter. So YAP used lib2to3. I like that. I understood why that was the case. But YAP was vulnerable to using older, buggier versions of lib2to3 when you were running on older Pythons. So I didn't want that. So Black bundled lib2to3 internally without the refactoring bits as blib2to3. But since I already bundled it, I could make some fixes and changes. So the fixes I upstreamed to Python, but the changes were kind of specific to how a auto-formatter wants its tokens and later on the nodes of the tree to be organized.
Right.
Specifically, the invisible braces that are emitted as indent and dedent are intermingled with whitespace and comments that might appear in your source code. And this might be somewhat confusing when you have a block comment after a block that is closed, like, I don't know, like an if statement with a trailer. So I made some changes to make it more obvious what is going on there, such that it was easier to write a formatter that maintains formatting of comments. But one thing that Black never maintained was backslashes. If it found backslashes in your source code, it would just indiscriminately remove them. I always found that backslashes in Python break this entire significant indentation paradigm of the language, since now you cannot really easily parse visually what you're looking at and judge what it's doing. So I wanted them gone.
Nasty.
Well, the reasoning was that all usage of backslashes I saw in actual user code were honestly unnecessary. This was just abuse because the programmer didn't know how to format something better.
Wait, Łukasz, can you hear that? It's Pedantic Pablo again. It's Pedantic Pablo. So yes, you remove backlashes, but you couldn't remove one.
Well, of course I remember this. I will remember this for as long as I live. So one particular case where I did remove backslashes too, but it turned out the consequences were a little annoying, was the with statement that used multiple context managers, better yet if they were named. So if you said with some context manager as C1, comma, some context manager as C2, colon, this is a lot of characters, right? So this was pretty likely to exceed your line limit that you set up. So you had to somehow... So what we did in this case for conditional statements was to use organizational parentheses. And it turned out the Python grammar, for whatever reason, just didn't have this ability for the with statement. So, such an oversight. We need to fix this. It should be easy, right?
Right.
And there was this new contributor, Pablo, that was interested in this. So I explained to him the problem.
Say the whole story. So mighty Łukasz invited poor Pablo to Meta's office in London. Wow. Such fancy place. There was a barista, like ice cream. And I was like, wow, man, this is the future. Nothing like the business boring shit that I work in Bloomberg.
I don't think you should be able to downplay Bloomberg's office.
No. Look, we don't have a barista in the office, so I was very impressed. Neither we have ice cream. So look, it worked. And actually, we don't have a canteen as well.
But you have a noise-canceling ceiling.
It's very impressive. The Bloomberg building is extremely impressive. But like, you did your part. And you invited me strategically in the day that they have pizza.
Right.
So you knew what you were doing. And then you invite me and then you say, man, like, look at this place. It could be yours only if you implement this feature. No, you didn't say that. But like, you nerd snipe me into this.
Yes.
Now you can continue.
And we both quickly discovered that, it's actually not that simple. And Pablo later discovered and explained to me that it's not just not that simple. Because we are using LL1, it's literally impossible for us to have organizing parentheses after the with statement. We do have them after the if keyword.
Right.
So what's the difference there? Well, first of all, you can have the opening parenthesis already being part of the context manager expression, but also there's this combination with the pesky as keyword used for naming the context manager within the with block. So when we have the LL1 grammar that can only look one token ahead, it is literally impossible for us to differentiate between a parenthesis that is part of the context manager expression and a parenthesis that is supposed to group multiple definitions of context managers using the as keyword for naming.
Actually, it's impossible with any LL parser. You need an LR parser here.
Oh, because of the left recursive.
Wait. Sorry. I have to say something. Sorry. Annoying Pablo has to say something. So I was super close to actually hack around, because this is what you do, right? When you cannot do the the legal way, you say like, okay, so how close can I get it? So I had a version that I presented to Łukasz, just to break his heart after he realized that we cannot use it. That it worked in all cases except for one, which is if you have a context, which I say like, man, who is doing this? Like this, nobody is doing this. This is the case when you have a context manager where the context manager itself is the keyword yield, right? But you cannot do that. So you cannot say with yield. That is illegal. You need to parenthesize yield. You need to say with open parentheses, yield, close parentheses, because that is a requirement of the thing.
Yeah.
And you say, why is that? Why would you do that? Well, it's because it allows you to send the context manager to the coroutine from the outside. So you can say coroutine.send open, and then you say open to the context manager. Wow. And they say, this is insane. Nobody will do that. And you know what? There was one single case in the standard library
That did that.
that was doing that shit. And it failed. So you couldn't run the Python standard library with that change. So we knew that we couldn't even say, who is doing this? No, because we were doing it. So
Yeah,
it
exactly
failed.
right. Well, we are now at an hour in this episode. So we're going to have to defer the story of how the new current parser came to be, how it works, and what weird new features of the language it enabled. But now, let's talk about something completely different.
PR of the week. Okay, so it has been an interesting period. Crazy stuff. I've been actually moving houses, which is a crazy thing to do. It went as insane as it could have been. So the PR of the week is a bit different. But I have one. It's PR GH113744, the best number. So let me tell you about this one, because this is very funny. This PR implements a new exception.
Ooh,
Wow.
You're adding a new exception.
So you can literally write this exception. And not only this is a special treat for our listeners, because only if you are listening to Core.py episode 7, you will know that this exception exists. And you will say, but why, Pablo? I mean, if you're adding a new exception, it's because people can use it. No, this exception will only be used internally by CPython. I mean, you can use it if you know it exists, but like I won't recommend it to do it. But you can type it in the REPL, for instance, or in your programs, and it will materialize by the art of magic. So the way you say you do stop iteration, now you can do incomplete input error. Wow.
Incomplete input error.
Let me tell you about the story of this PR. So there is this, this will be even more clear when we talk about the back parsing in another episode, but there is this little module in CPython called CodeOp. And CodeOp is part of something else, which is the code module, which allows you to implement like REPLs. Like, for instance, you want to embed a Python-like REPL inside, I don't know, SQL or something like that, SQL Alchemy or something like that, right? So you can like hack the REPL around and maybe change the headers and a bunch of things, right? And what these do to be able to implement the REPLs is that you need to know if a given string it could be Python code. Because why is this needed? Because let's say you do function definition, right? And then you type like the start of the definition. So def f parenthesis colon, and then you press enter.
Yeah.
Then you press enter. So you gave this string to me. I'm the parser, and I need to see is more going or is just this wrong? Because if it's wrong, I need to tell you your stuff is wrong. But if it could be more going, that could make it correct. I need you to allow to continue writing, right? So in the REPL, that will be the 3 dots at the beginning, like more input is going, right?
Yes.
But for that, I need to know if that string that you give me could become valid Python code or not.
So it's not syntax error. It's something that it's incomplete.
Exactly. So if you just give me the start of the function definition by itself, it's a syntax error because it's missing the actual body of the function. But if you're typing it in the REPL, I need you to allow, continuing going. Because every time you press enter in the REPL, you kind of compile that code, right? But if it's incomplete, I need to ask you for more. This is totally different how a file is parsed, because a file is parsed from beginning to top. So you just give me half of a function definition, that's wrong. What is the other one, right? What is the other half? But here, the REPL needs to do that. So the way the CPython REPL does this is for another episode. It does a bunch of stuff. But the way the code op does is that there is this insane algorithm devised by Tim Peters. It compiles it several times with new lines added and non-new lines added, and like it checks the syntax error, if it's syntax error, if it's like end of file, and it has some magic and heuristics that break every single time we change the parser. So we add a new error condition, or we add like better error messages, and it just breaks code up because it's super flaky. This algorithm is not real. It's not a real algorithm. It's just doing a bunch of like, well, if I add a new line, it shows me this error. It may be incomplete, or like, meh. So that was really bad. So we changed this, and then we say, okay, you can, I'm not going to say how, but you can run the parser in a specific mode. It's secret. So you can run the parser in a secret mode that will allow incomplete error. This means that if you gave me half of a function definition, it will say yes, instead of saying syntax error.
Right.
But the problem is that the way it communicated this before is by erasing a syntax error with the text incomplete input. And the code op module was checking the
string.
The string, which is not good, because if someone somewhere implements a syntax error that says incomplete input, blah, 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 then it will trigger this, right? So that was bad.
Yeah.
And it was super annoying to maintain. So now it does the correct thing, and it communicates incomplete input by raising an exception that is called incomplete input error. So now we properly catch that exception, and we know that, okay, it's this one, and it's not because someone added the text incomplete input to something else. And this was important for things like f-strings, because f-strings contain the string incomplete input when they fail, like when you don't close the string, right? So it says incomplete input detected a line, whatever, right?
I love it.
So there was a bunch of bugs around that.
My only piece of feedback is that you missed a wonderful opportunity to name this exception incomplete input error. Because it's incomplete input error.
Well, the exception in C is called PyR incomplete input, right?
All right, but details.
Okay, but this now, question, wow. Łukasz, how many subclasses of syntax error there are? I mean, without counting with this one, because this is a subclass of syntax error.
I would say there's like 3, I don't know.
There is 2. There is one subclass of syntax error, and then there is another subclass of that subclass. What is a more specific syntax error that comes to your mind?
Well, like indentation error.
Indentation error! Yes! But what is the subclass of indentation error? There is one subclass of indentation error.
Well, like, I hate tabs.
Tab error, very good. I'm very impressed. This was a tough one. Wow, you just recovered your employment. This is very impressive.
Yeah. So tab errors actually I witnessed. So yeah, if you're working on like other formatters and whatever, you grow to understand why you had to choose between either allowing only tabs or only spaces, like allowing both. That was a world of pain.
There is someone who opened an issue about this and like how inconsistent is the error. Sometimes we raise tab error or indentation error, depending if you put like the tab and then the spaces or the spaces and the tab, like in 2 lines. I don't know. Like,
and this brings us to talk about what is actually happening these days.
Yeah.
What's
going on
in CPython? We just landed the huge JIT PR that was released, that was opened on Christmas Day with this large poem as a description and 400 commits and so on, and which also have...
So how fast is the JIT, Łukasz? How fast? Quickly.
It's almost not slower. It's just a little slower.
Wow, very impressive.
Yeah, we're going to get to how we're going to get it faster. But before we get there, let me just say, Python is testing very many things in the world. It is a test suite for a bunch of industries. And one of those industries is github.com. With this one PR, we again broke GitHub. When Brand pressed the green button went gray and then errored out.
Nice.
And then we actually saw that the PR is integrated into the Git repository, but the PR stayed open.
We did.
It was still open and you could still press the green button again, but now you couldn't because it was badly conflicting. It was like, oh no, now you have to fix this
It was
huge
conflicting with itself.
conflict with yourself, which should actually resolve to nothing, right? It should be just a but no, like GitHub essentially broke for this. And I don't know, the change was so big, or I don't know what that was, or there was some outage at the same time. It was just super bad timing. Hard to tell. The only thing that we know is that Brand in the end just closed the PR. So the PR is sad red. It looks like it's not merged, but it is. So it's one of those things where we use tooling. The tooling is not perfect. We are sometimes stressing it to its limits. Right, but before we get to making Python faster with the JIT in place, let me talk about my favorite topic, which is free threading. So first of all, Sam Gross, who is responsible for actually spearheading this, starting PEP 703, and before that, actually making this entire proof of concept of 3.9 without a GIL, and later on 3.12 without a GIL, is now being nominated as a core developer. The vote is open, so anything can happen. But, in all likelihood, we're going to get a new core developer in a week. So
Well done.
Fingers crossed. The vote is open at this point.
Nah, he's going to do it.
Sure.
He's fantastic.
Yeah,
Well done, Sam.
it's a formality for him, but also a formality requires me to just still say, well, anything can happen. It's also like
Anything can
I am on the program committee for PyCon, so even though it's all pretty much decided at this point, I still need to tell you, anything can happen still, but no, we already know. But anyway, a bunch of changes that are some of the most tricky landed now for free-threaded Python. So stop the world pauses that we talked about being implemented are now landed. So that's the things that we need for cyclic garbage collection, for shutting down the interpreter, and before calling fork. So as we mentioned in previous episodes, there are per interpreter pauses and actually global per process pauses. And with that having implemented, we now actually have a working garbage collection for free-threaded builds.
Yes.
And that is very impressive because this is the one that required memalloc because it's using memalloc APIs to traverse heaps and not the PyGC head linked list that we had before.
Yeah, that was a tricky change for him to do. I reviewed that on a bunch of different PRs. He did like 2 or 3. He splitted the first one in like the GC module into several. So it was nicely done, like in the sense that he didn't do it in one go. It was trickier than it looked like because it turns out that we were using the GC stuff for the trash can mechanism. We can talk about that in another episode.
Yeah, we should, yes.
And now we needed to adapt the trash can mechanism to the new stuff. But that was a bit of unexpected fallback. But that is done, so...
Right. So obviously, if we are using memalloc APIs to do the garbage collection, we need to put the objects in the right heaps. So now we use GC heaps for GC allocations with a thread local that you have called current obj heap. You have this variable to know where you actually instantiate new objects now. And a bunch of things that are in the standard library got thread safe. So q.simpleq is now thread safe. It uses a ring buffer for storage. That's a separate change, but both impressive. List objects are being made thread safe. This is actually more complicated than it seems because in Python they are very central to the language. So they're implemented in a bunch of places and they have a rather large API as well. So we already have a bunch of things landed for thread safety there, like pop, clear, reverse, remove, wrappers, length, and so on. So there's a bunch of things left, like append and slices. But this is already a ton of good work by Dong Hina. So I love to see the progress. Dictionary versioning uses atomic increments now, and element tree iter parse was a funny reference cycle that caused an edge case in the in the test suite that we had in the free-threaded build. So now the reference cycle is avoided, and we no longer have this resource warning raised during tests, which gets transformed to an error on buildbots and obviously causes issues. Yeah, but enough about that. Let's talk about making Python faster, okay?
So for the faster CPython side, we have a bunch of changes that sound like magic spells and whatnot. So one of them is, the most important one is that types in the interpreter DSL, so we talked about this in several updates in the past for the tier 2 optimizer. So now they will allow annotating that after an operation that is done, we know what the type will be. This includes also 64-bit refinement information, which is a bit tricky to get, and which is also like is fetched from the previous operand when you do that. So for example, for the binary op-add float, that is the specialized version of binary auth for floats. So when you have two floating point numbers and the interpreter uses a specialized instruction for floats that don't apply obviously to other things, the operation, we know the result will be a float, because when you add two floats, there is a float. This is not always the case, right? Because integers can overflow and whatnot, but floats yield floats, so that we know. So we can use these things. And in this case, there is now the ability to mark instructions are pure. That means that they don't have side effects. And when you have instructions that they don't have side effects, you can optimize like knowing that. For instance, you can cache the result and use it in the next time, which obviously you cannot use if you know the side effects. For instance, one of the instructions that do this is swap. So when you have like two variables on the top of the stack and then you want to swap them. This is used, for instance, when you do a comma b equals b comma a. So the next big thing that the faster CPython team is working on, which is a huge thing that we are working towards, is called trace stitching. And we have down here is like more steps toward achieving this. In particular, this idea of trace stitching is about optimizing the less common failure modes for traces that we are taking. So for example, if you have a conditional branch, that is not taken as part of the trace. So you can think here, for instance, if you have a conditional and then there is like a condition that is more common and that trigger like an optimized version of this, which will go into what we call the tier 2 interpreter. We have talked about the tier 2 and tier 1 in previous episodes. But if sometimes you have a branch misprediction, for instance, you take the less common branch here, you will need to go to tier 1, and because like that is something that we don't have. And then if that is hit and like if that is visited enough times, the tier 1 interpreter will create another trace, and it will create a new version of this in the tier 2 interpreter. The problem here is that if you go through this condition again, you will go to the faster tier 2 interpreter, it will hit the branch misprediction again, it will go to tier 1, and then it will go to the new optimized trace that we have in tier 2. So you need to jump from the second tier to the first tier back to the second tier, and that is obviously inefficient. So this idea of trace stitching is basically redirecting the first tier 2 to the second tier 2 version. So even if there was a jump in the tier 1 interpreter in the middle. So basically it's basically avoiding some overhead from the fact that we had to de-optimize and then optimize again.
Yeah, very cool.
So we basically put the two traces one after the other. Cool. And to make this work, basically Mark Shannon, our magician of making ginormous pairs and very useful ones, he has to ensure that all executors, and here executor is a fancy name, so basically Mark Shannon added this ginormous, I don't think it's public, I think it's semi-private API for code executors. Right. So now basically you have an abstract way to add pieces of pluggable code that can optimize Python. So this is in case other people want to have JIT compilers, or Python wants to add something, or MyPyC in the future or something like that. So this is abstracted away, and this is what Mark Shannon called executors. So basically, we need to ensure that all the executors are making progress. So as we are advancing and we are optimizing these traces, we call these executors to do something with the bytecode, and then we need to ensure that they don't go into loops, or they don't do anything, or they loop around and they do no ops. And for that, the way that he's doing this is that basically checking that all of them are doing it. So this proves that every subgraph of all these executors will advance, which sounds very simple, but it's quite a big PR. And this is just to ensure that we don't de-optimize the whole thing.
Some changes, in fact, just like Mark's change, are very simple to explain. This is what we did, but they were very complicated to implement. So one of those that was surprisingly gnarly was ntpath, .isReserved. So we have now a new function, and it just tells you whether on Windows some path that you want to use is invalid for users because it's special, right? If you, for example, wanted to have con as a file name or whatever. So that took almost 2 years to mature, and it's now implemented by Barney Gale. So like kudos.
Nice.
Because it turns out the rules for which names are reserved are very complex and even change between Windows versions. So actually, to not mislead the user and return something that is invalid for the particular machine that you're on was not very easy. So it's pretty cool that we have it now.
Well done.
So one last thing that I wanted to mention was a bug fix that I got pinged about too, which is for embedded interpreters. Python 3.12 started using way more memory than 3.11 and before. And the reason was sub-interpreters had things moved to make them actually more isolated. When a sub-interpreter got destroyed, malloc memory didn't get freed, so until the process was actually shut down, you could have this unused memory that was just kind of useless for the process anymore, inaccessible by the rest of the interpreters. It used to be that it wasn't the case because the main interpreter in the process would reclaim this memory. So now Neil Schemenauer landed a complicated patch to sort of kind of reverse the change that was made before, but in a way where the isolation of the sub-interpreters is preserved.
That's very
that was also a big achievement, I guess. The issue is still open, but it's open in the sense that this situation wasn't perfect in 3.11 and before either. Like there were cases where still having sub-interpreters shut down would leave some memory unusable for the rest of the process anymore, but still allocated. So this is still investigated by Neil, but we are actually now in a case where we're not worse than 3.11 anymore. So I like this.
3.11 is very cool. I don't know why a new version will be worse. But the last thing that I want to say is that in this PR that we mentioned back in episode 1, I think, about adding DWARF support to the perf integration for Python. So I've been making a lot of great progress. We are quite close. I'm working with someone from the Linux kernel. So this person who, unfortunately, I don't think I can properly pronounce the name, but it's called Nanghyun Kim. So that's the best approximation I can do to pronounce this. So he's a lovely person from the Linux kernel focusing on the perf tool. He's been working with me on, integrating DWARF support, which is quite tricky. But I'm very happy to say that we have found 6 bugs in the Linux kernel so far.
So not just GitHub, we are now the test suite for Linux kernel as well.
Yes, it turns out that the interface that we plan to use for adding DWARF first, it's only used by V8, so the JavaScript JIT compiler. So it's only used by them, and it has bugs in many places. So there is bugs in the documentation, there is bugs in the code, there is bugs in the integration, there is bugs in how the Linux perf tool creates ELF files. But this is very cool. We've been fixing all of this. We missed one of these merge windows because the Linux kernel has those. So we missed that. But he's also, we are submitting the patches to the new merge window. So hopefully they'll land in, I think it's 5 something and 6. So quite cool. It's super fantastic to work with this person. So kudos to him. And we are fixing the Linux kernel apparently. So and even more. But who knows how many bugs we found here? This has been a gold mine. But yeah, very excited. We will get there.
Wow, this is very impressive. And the perf improvements, that's going to be very useful for all server usage as well. Like DWARF is black magic to me, so I'm very happy to have somebody else handle this. Well, as long as it keeps working when we actually enable the JIT.
Oh, we will see about that.
We'll see.
Yeah, cliffhanger, eh? You know how to set them up.
Yeah, that's just one cliffhanger. And the other one is, how does the parser actually work these days in Python? And for this, you're going to have to join us for another episode in 2 weeks. Until then, see you next time.
See you next time.